Welcome to our comprehensive guide on Python interview questions focused on data structures and algorithms. This series is designed to help you master the essential concepts that frequently appear in coding interviews. Today, we'll cover advanced Python features like list comprehensions, decorators, and generators, along with popular data science libraries like Pandas and NumPy. These topics are crucial for anyone preparing for Python developer positions, data science roles, or software engineering interviews. Understanding these concepts will not only help you pass interviews, but also make you a more effective Python programmer in real-world projects. List comprehensions are one of Python's most elegant features that allow you to create new lists in a concise and readable way. The basic syntax follows this pattern: expression for item in iterable if condition. Instead of writing multiple lines with a for loop and append statements, you can accomplish the same task in a single line. For example, to create a list of squares from 0 to 4, the traditional approach would require initializing an empty list, then using a for loop to append each squared value. With list comprehensions, you simply write x squared for x in range 5. This creates the same result, but is more concise and often faster. List comprehensions are not only more readable, but also generally perform better than equivalent for loops, making them a favorite among Python developers. Decorators are a powerful Python feature that allows you to modify or extend the behavior of functions without permanently changing their code. A decorator is essentially a function that takes another function as an argument and returns a modified version of that function. The concept follows a wrapper pattern, where the decorator function contains an inner wrapper function that can execute code before and after the original function runs. To use a decorator, you simply place the @ symbol followed by the decorator name above your function definition. This is syntactic sugar that makes your code cleaner. Decorators are commonly used for logging, timing function execution, authentication, caching, and many other cross-cutting concerns in software development. They provide a clean way to separate these concerns from your main business logic. Generators are special functions in Python that return an iterator, producing values on demand rather than creating all values at once. The key difference between regular functions and generators is that generators use the yield keyword instead of return. When a generator function is called, it doesn't execute immediately. Instead, it returns a generator object that can be iterated over. Each time you request the next value, the generator resumes execution from where it left off until it encounters the next yield statement. This makes generators extremely memory efficient because they only generate one value at a time. For example, a generator that produces numbers from 0 to n will only store one number in memory at any given time, compared to a list that would store all numbers simultaneously. Generators are particularly useful when working with large datasets or infinite sequences. Asynchronous programming with async and await is a powerful paradigm in Python for handling input-output bound operations without blocking the execution thread. When you mark a function with the async keyword, it becomes a coroutine that can be paused and resumed. The await keyword is used inside async functions to pause execution and wait for another async operation to complete. This is particularly useful for operations like file reading, database queries, or network requests where your program would otherwise sit idle waiting for a response. Instead of blocking, async functions can yield control back to the event loop, allowing other tasks to run. To run an async function, you typically use asyncio.run. This approach can significantly improve the performance of applications that perform many input-output operations by allowing multiple operations to run concurrently rather than sequentially. Context managers in Python provide a clean way to manage resources by ensuring proper setup and cleanup operations. They are commonly used with the with statement to guarantee that resources like files, database connections, or locks are properly released even if an error occurs. To create a context manager using a class, you implement two special methods. underscore underscore enter underscore underscore and underscore underscore exit underscore underscore. The enter method is called when entering the with block and typically returns the resource to be managed. The exit method is called when leaving the with block and handles cleanup operations. It receives information about any exceptions that occurred. Context managers are essential for writing robust Python code because they prevent resource leaks and ensure consistent cleanup behavior. Common examples include file operations, database transactions, and thread synchronization primitives. Advanced decorator patterns take the basic decorator concept further by supporting parameters and chaining multiple decorators. Decorators with arguments require a three-level function structure. The outermost function accepts the decorator parameters, the middle function is the actual decorator that accepts the target function, and the innermost function is the wrapper that gets executed. This pattern is useful for creating configurable decorators like timers with custom names or retry mechanisms with specific parameters. When multiple decorators are applied to a single function, they are executed in reverse order, similar to mathematical function composition. The decorator closest to the function definition is applied first, then the next one up, and so on. Understanding decorator chaining is crucial for complex applications where you might combine logging, timing, authentication, and caching decorators on the same function. Pandas is the cornerstone library for data manipulation and analysis in Python, built around two primary data structures, series and data frame. A series represents one-dimensional labeled data, similar to a column in a spreadsheet, while a data frame represents two-dimensional labeled data, like a complete spreadsheet or database table. These structures are designed to handle real-world messy data with features like automatic alignment, missing data handling, and flexible indexing. Creating a data frame is straightforward using the Pandas .dataframe constructor with a dictionary where keys become column names. Essential operations include head method to view the first few rows, info method to get a summary of the data frame structure, and describe method for statistical summaries. Pandas provides intuitive methods for filtering, grouping, and transforming data, making it indispensable for data science workflows. Data manipulation is where Pandas truly shines, offering powerful tools for filtering and aggregating data. Boolean indexing allows you to filter data frames using logical conditions. You create Boolean masks by applying conditions to data frame columns, then use these masks to select specific rows. For multiple conditions, you combine them using ampersand for and, pipe symbol for or, and wrap each condition in parentheses. The group B operation is fundamental for data analysis, allowing you to split data into groups based on column values, then apply aggregation functions to each group. The ag method accepts a dictionary mapping column names to aggregation functions like mean, sum, count, or max. This pattern of split-apply combine is essential for creating summary statistics, generating reports, and understanding patterns in your data. These operations form the backbone of most data analysis workflows. NumPy, short for numerical Python, is the foundation of the scientific Python ecosystem, providing high-performance operations on multi-dimensional arrays. The core data structure is the end array, which stores elements of the same type in a contiguous block of memory, making operations much faster than standard Python lists. Creating NumPy arrays is simple using the array function, and you can inspect their properties using attributes like shape, which returns the dimensions, and dtype, which shows the data type. NumPy arrays support element-wise operations, meaning you can perform mathematical operations on entire arrays without writing explicit loops. For example, multiplying an array by 2 automatically multiplies every element. This vectorization capability, combined with NumPy's implementation in optimized C code, makes it significantly faster than pure Python for numerical computations. NumPy forms the foundation for other scientific libraries like Pandas, Matplotlib, and scikit-learn. Algorithmic thinking is the systematic approach to problem-solving that breaks complex problems into smaller, manageable steps. This mindset is essential for coding interviews and software development in general. The process typically follows several stages. First, thoroughly understand the problem by identifying inputs, outputs, and constraints. Second, plan your solution by considering different approaches, analyzing their trade-offs, and choosing the most appropriate one. Third, implement your solution step by step, starting with a basic version and then optimizing. Fourth, test your solution with various inputs, including edge cases. Good algorithmic thinking involves recognizing common patterns like iteration, recursion, divide and conquer, and dynamic programming. It also means considering time and space complexity from the beginning, not as an afterthought. The example shows a typical pattern of initializing a result container, iterating through input data, applying conditional logic, and processing matching items. Time and space complexity analysis is crucial for writing efficient code and succeeding in technical interviews. Time complexity measures how the runtime of an algorithm grows with input size. Common complexities include constant time O of 1, where operations take the same time regardless of input size, like accessing an array element by index. Logarithmic time O of log n, where time grows slowly with input size, typical in binary search algorithms. Linear time O of n, where time grows proportionally with input size, like iterating through an array once. Quadratic time O of n squared, where time grows with the square of input size, common in nested loops. Space complexity measures memory usage. O of 1 space means using constant extra memory regardless of input size. O of n space means memory usage grows with input size. Recursive algorithms often have space complexity equal to their maximum recursion depth. Understanding these concepts helps you choose appropriate algorithms and optimize your code for better performance. Mastering these fundamentals will significantly improve your problem-solving skills and interview success.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.